Okay, so today we're going to do limits at infinity. Example 1 says evaluate the following limits. If the limit does not exist, explain why. So go ahead and do A and B. This is what we did yesterday, and then I'll do C and D with you guys. All right, go ahead and group up. I guess there's only 30. So go ahead and form one big group. See if you guys agree. See if you approach this the same way. If you approach this in different ways, talk about how the different ways that you approach this.
So the first one I just decided to do it graphically because it was visible on the graph, and then 2 was the 8. The second one I did it algebraically. Since it's really only going from left, I said to do approach from left, and I got 32 from that.
Finished too fast. As you said, graph the table.
Okay.
Okay, so we have the limit as x approaches 3 of 2x. What'd you guys get? 8. Since you guys worked in one group, I'm going to assume that you all agree. I would do this one graphically just because I have the graph there. X equals 3 is there, and the 0.38 is on the graph. So I can just pluck that right off. Part B says the limit as x approaches 5 of 2x. What'd you guys get for this? 32. If you do this graphically, if you go up on the graph, you don't see 32 up there. So using the techniques we have learned so far, we can't really use graphically. So we have to do more of an algebraic t-table approach. Later on, we'll learn some techniques that make this limit a lot quicker. But for right now, we need to make a t-table. So t-table, I would do a 4.9, 4.99, 4.999, skip over 5, 5.001, oops, 5.01, and I ran out of room, but I would normally do 5.1 as well. So if I plug those in, 4.9, I get 29.9. For 4.99, I get 31.8. For 4.999, I get 31.98. So I'm getting closer and closer and closer to 32. And then if I come in from the other direction, at 5.1 or 01, I have 32.22, and then I have 32.02. So I'm getting closer and closer to 32 as well. So we have 32. And if we had evaluated our graph at 5 or our function at 5, it would have been 32. But again, for limits, we don't really care what's happening right there. We care what's happening around it. So we don't really care what's happening there. But it is 32. Like I said, a little bit later, we're going to learn techniques that make this a lot easier. Then part C says, what is the limit as x goes to infinity of 2x? So remember how yesterday we had limits as x approaches a number, and if x approached a number, it went to infinity, we had a vertical asymptote. Well, something kind of different happens here. In this case, we're letting our x values get really, really big. And so we're going to make a t-chart for that as well. So our x and y. And typically when I go to infinity, I start around 10. I then go up to 100, 1,000, and then maybe 10,000. To see if I notice if this graph is leveling off, is it shooting up, is it shooting down? What in the world's kind of going on with it, or is it oscillating? And you can normally get that picture by just tacking on a 0 each time. So at 10, we have 1,024. At 100, we have 1 times 10 to the 30th power, meaning I have a 1 with 30 zeros behind it. That is huge. And then if you try to calculate this with 1,000 in your calculator, this is too big to calculate. And then if you try to plug in 10,000 into your calculator, it is even bigger. So I'm just going to put even bigger. So as I'm letting my x values approach infinity, my y values are getting bigger and bigger and bigger, so they are also approaching infinity. And so my limit as x approaches infinity of 2x is infinity. And we can look at the graph as well. If we were to trace this graph, notice that it's just getting steeper and steeper and steeper. It's never really it's never going to turn around. It's never going to level off. It's just shooting up and away to infinity. And so graphically, we could have said this also goes to infinity. Okay, any questions about that? Well then, if it's going to infinity when our x's are going to infinity, what is it doing when our x's are going to negative infinity? Go ahead and try this. All right, go ahead and group up and see if you guys look at this the same way.
So I did the exact same parts of the algebraically, and as I got closer to negative 1,000, negative 10,000, it was instantly zero. And you can look at the graph and see it just flattens out as well.
All right, what do you guys get?
Zero.
0. All right, we can do this graphically. If we start going and moving to the left of the graph, it kind of flat lines and it flat lines at 0. So 0 makes sense. Again, if you're given a graph, feel free to use it to your fullest ability. If you're not given a graph, we'd have to make a t-chart. So XY. Look at maybe negative 10, negative 100, negative 1,000, maybe negative 10,000. And our values, when we plug this in, is negative 0.00098. Then we get 8 times 10 to negative 31. If you get that number, that means we moved the decimal point to the left 31 times. So there are 31 zeros in front of that 8. It's a lot of zeros. And then if you plug in negative 1,000, my guess is your calculator just says error or too small or something like that.
It just said 0.
It just said 0. Yeah, so it's small enough that it's not even give you the actual number. So I'm going to say tiny. And I'm going to say even smaller. So it never actually, even though your calculator says 0, it never actually hits 0, but it's so close that it might as well be 0. And so what's kind of nice is if you remember from pre-calc, we always talked about that end behavior and we looked at polynomials and we said, oh, if the power is odd, then you have an end behavior that looks like one side going down and one side going up. If it's even, both sides are going up or both sides going down. And you just kind of had to memorize that. Well, in calculus, these limits as we're going to infinity is what the end behavior of the graph is doing. So now I can ask you, what is the end behavior of this function doing? And you can just use a limit. Limit as x goes to positive infinity, limit as x goes to negative infinity. So that is a note. As x goes to infinity, or as x goes to negative infinity, we are looking at the end behavior. Of the graph. So a nifty way to word this on the test would be, hey, what is the end behavior of such and such? And I'm just really looking for you to take the limit as it goes to infinity. Any questions about that? All right. Example 2. Has given that f of x equals x squared over x plus 1 squared. Find the limit as x goes to infinity of f of x. So we can make a table if we want to, or we could look at the graph. So if we make a table, make an XY table, we're looking at 10, 100, 1,000. And if we plug these numbers into our function, you'll get 0.83, 0.98, 0.998. And so what is that getting? What are those y values getting closer and closer to? They're getting closer and closer to 1. And we can see that graphically. So if we look at this, notice it bounces at 0 and starts to kind of level off at 1. So it flatlines at 1. So something that we can say is we have a horizontal asymptote at y equals 1. And so the limit as x goes to infinity of f of x equaling 1 is the same thing as saying that we have a horizontal asymptote. And so if you had one of those problems like we did yesterday where I gave you a bunch of limits and a bunch of points and I said, make a sketch of this graph, I could now add in horizontal asymptotes into that. And so your graph would have to level off at a certain point. All right, go ahead and try B. All right, go ahead and group up and see if you manage to do this the same way. If you did this different ways, talk about the different ways that you could have approached this problem.
I just did it briefly again and notice that as you're decreasing, it's also getting closer to one first one. Then you can also see it appear on the graph. That's not crossing that. It's on last job. That's fun with that. At least that's how I saw it.
There's 92 degree.
All right. So what'd you guys get?
1.
1. Everybody in the group agree? Okay. So if we want to do this algebraically, we notice that this comes down, but notice that it kind of levels off around 1. So that limit as it's going to negative infinity is 1. If you wanted to do this algebraically, create a t table and probably do -10, -100, -1000. And we'd have values such as 1.23, 1.02, and 1.002. Everybody agree with those numbers? Okay. Sometimes my notes are off. So if you disagree, that's fine too. So as these top numbers are getting smaller and smaller and smaller, and they're going to negative infinity, as they're going to negative infinity, my y values are going closer and closer and closer to 1. And so what that tells us is that the limit as x goes to infinity of our f of x is 1. And if you look at the graph, you notice that there is a horizontal asymptote at 1. So horizontal asymptote at y equals 1. And so that limit statement and that horizontal asymptote statement, they're the exact same thing again. So kind of a key note on this page is if we have a limit as x goes to infinity of f of x, and it equals some number, or we have the limit as x goes to infinity, or negative infinity, excuse me, of f of x, and it equals some number, then f of x has a horizontal asymptote at y equals n. And n is just some number. But it has to actually be a number. So our next example, example 3, we'll see that sometimes they don't always equal a number and they don't always have that horizontal asymptote. So example A says find the limit as x approaches infinity of f of x. And so we're going to do this algebraically. We have x and y. And we're going to look at numbers like 10, 100, and 1,000. And when we plug these numbers in, these numbers, if you look at our piecewise function, these numbers are greater than 2. So we'll plug these into that bottom function. So I'm going to pull out my handy dandy calculator. So if I was to plug 10 in, I would have 8 minus 10. And that gives me my -2. If I plug in 100, again, I'm going to plug it in into that bottom equation. So I have 8 minus 100. I get negative 92. For 1,000, again, 1,000 is bigger than 2, so we're going to plug it into that bottom equation, and we have 8 minus 1,000. And I get negative 992. So is that approaching a number?
It's approaching negative infinity.
Yeah, it's approaching negative infinity. So as my x values go to infinity, my y values are approaching negative infinity. And we can see that graphically as well. If you look at our graph to the left of 2, it just shoots down. And it keeps shooting down, shooting down, shooting down. So what that tells me is that my limit as x goes to infinity of our function, this equals negative infinity. Questions about this? Sometimes when there's a lot of infinities flying around, it gets a little confusing what is going to what. So any questions at all? Okay. Just remember that the piece on the right-hand side of the equals, this is where my y is approaching. And then down here below my limit sign, this is what x is approaching to. So as x is going to infinity, y is going to negative infinity. We don't have any horizontal asymptotes here. It doesn't really exist on the real number lines. So it goes to negative infinity. Okay. Part B says find the limit as x goes to negative infinity of f of x. So go ahead and try this one. Give you guys a few minutes to try part B. right, go ahead and get in your group and see if you guys agree, see if you guys did it the same way.
So, I did it algebraically again, and also I noticed graphically that it's increasing to infinity as it's going to negative infinity. So, but I guess for the answer, I got infinity.
Okay. You guys are so non-chatty. All right. So if we did this graphically, we're going to negative infinity. So you can notice that it just kind of shoots up, and it shoots up to positive infinity. So our answer is positive infinity. And then if I wanted to do this algebraically, because your teacher's mean and she said you had to do this algebraically on a test, I'd make a t-chart. And I'd probably do -10, -100, -1,000. But if your teacher was mean and didn't give you a graph, you'd have to figure out which one of these to plug it into. I'm going to erase some of this. And you're looking at numbers smaller than 2. So since we're looking at numbers smaller than 2, we're going to plug them into that top equation. So just kind of be careful which equation you're plugging your numbers into. When we do that, we get 51, 5,001, and 500,001. So they're getting bigger and bigger and bigger. As our x values go to negative infinity, our y values are shooting off to positive infinity. And so what we can say is that the limit as x goes to negative infinity of f of x is infinity. Again, I know a lot of infinities are kind of flying around here. So just remember that on the right-hand side of the equals, this is what your y's are doing. And then over here, down here, is what your x's are doing. Okay. All right. No questions? Questions? Maybe questions? You guys are so quiet. It's weird. My morning class is so chatty that I'm yelling over them for most of the time. So it's like, you guys, like, are you awake? All right. So example 4. For the given function, f of x equals sine of x, find the limit as x goes to infinity of f of x. So if we're looking at this, notice that the sine function, and remember this from pre-calc, the sine function is oscillating. So looking at this graphically, is there going to be a limit? No. So I can go ahead and say the limit as x goes to infinity of f of x. I'm just going to go ahead and put sine in there so you guys can see a different notation. Of sine of x does not exist. And it does not exist since the y values jump from -1 to 1. It's always jumping back and forth. It's never settling down. It's never calming down. It's like a little wild child. And you never calm down. All right. Well, that's graphically. What about algebraically? What would it look like if we did 10, 100, 1,000? So let's look at this. If we made an XY table, and sine curves are sometimes tricky, 10, 100, 1,000. If I plug those numbers in, I would get negative 0.54, negative 0.51. So if you just did two numbers, it almost looks like it's approaching something. It almost looks like it's approaching negative 0.5. So especially with sine curves or trig functions, you want to keep doing a few more. If I do 1,000, I get 0.83. It's like, oh, okay, there's something that's a little different. And if you're still not convinced, and it's like, okay, maybe that's an oddity and that the rest of these will calm down, do 10,000. And if you do that, you get negative 0.306. So you can't really see that it's bouncing necessarily, but you can see that it's not approaching a number, not shooting off to infinity, not shooting off to negative infinity. It just doesn't exist. Kind of makes us sad. So as our X values are going to infinity, our Y values are bouncing. Just gonna put bouncing there because there's no consistency to them. Okay, any questions about that one? All right. So for example 5, we have another trig function, but this case we have sine of x divided by x. And we want to find the limit as x goes to positive infinity. So if you're looking at the graph, you see it comes up here, see it dips down, but we don't know if the graph is zoomed out enough. Does it shoot back up and then come back down? Is it leveling off? What is this doing? So graphically, we're kind of out of luck. We can't really tell what this is doing. If you zoom out on your calculator, the graph gets really wonky and you're just not able to tell. So let's go ahead and go to algebraically and build a chart. Let's do 10, 100, 1,000, and 10,000. If we plug in 10 into our sine of x divided by x, a side note, you want to be in radian mode. You'll get way different answers than if you're in degree mode. You get negative 0.05. At 100, you get negative 0.005. At 1,000, you get 0.0008. And at 10,000, you get negative 0.00003. So it's jumping over the x-axis and coming back down. But when it's jumping, the jumps become less drastic.
So it's gradually approaching zero again.
It is approaching zero. I kind of look at it like if you're, I don't know if you guys are big boaters, but if you're on a lake or if you're on a river or something and you're catching these big waves on a boat and all of a sudden it turns into glass and it flattens out. And it's like, oh, the waves are going to slowly get less drastic and it's going to even out to zero. So that's kind of what's happening here. It'll jump up and jump down and jump up and jump down, but it's gonna kind of just flatten out towards the end. So as our x's approach infinity, our y's are approaching zero. And that is really hard to see graphically. Algebraically, it's still kind of hard to see because it's like, oh, positive, negative, negative, positive, negative. What's going on there? But if you look at the numbers themselves, the numbers are getting smaller and smaller and smaller and smaller. So we say that the limit as x goes to infinity of sine of x over x is equal to 0. And since it equals a number, what we can say is that our function f of x has a horizontal asymptote at y equal to 0. Pretty nifty. Okay, questions?
So if it's basically just a straight